Hello everyone, welcome back to another video on Aspen Tech channel, and today we will be discussing the calculations of Exergy using Aspen Plus. So Exergy is an important concept because it is used, analyzed to evaluate the performance of various chemical processes. Even in research, in design, in optimization, this factor plays a vital role. It consists of four factors. Number one is physical exergy, number two is chemical exergy, number three is kinetic exergy, and number four is potential exergy. Usually, in the calculations, kinetic and potential exergies don't play a vital role, or this significance is very small. So, in this calculation as well, we will be ignoring the impact of kinetic and potential exergy. So, effectively, we are left with physical exergy and chemical exergy. Now, physical exergy is calculated as H minus H naught minus T naught S minus S naught. Obviously, H represents the enthalpy of the stream at the given condition and enthalpy at the reference condition. And obviously, we know the reference conditions 298.15 Kelvin or 25 degrees centigrade and 1 atm. And similarly, this one represents the entropy. For the chemical exergy, the formula is summation of this summation shows the number of components in the system. We will start today with a very simple example where we will be taking the one component. But once we have more than one components in the system, in the simulation system, then we have to use this summation. Summation xi, which represents the mole fraction, E of chi, which represents the standard chemical exergy of the component. Basically, this vector, for example, if it is water, it will be xi, and that will be the standard exergy of water. Similarly, if it is nitrogen, if it is air, accordingly it will be calculated. Plus R, which is the ideal gas constant, T naught, which is the reference temperature 298.15 Kelvin, and again xi, natural log of xi. So overall, this parameter of chemical exergy is divided into two terms. Once we will be calculating, this will be the first term, and this one will be the second term, and in that we will sum it up. And obviously the unit should be consistent, so we will also see this impact over there. Then percentage exergy efficiency for a equipment or a process is calculated as total exergy out divided by total exergy in, obviously multiplied by 100. Definitely that is also there. And exergy destruction is equal to total exergy in minus total exergy out. So these are the standard formulas which are used to calculate the exergy efficiency, exergy destruction rate in a process. But obviously before that, we need to calculate physical exergy and chemical exergy of a process stream, which is at inlet at outlet. So this is a heat exchanger example which we have been given, that we have been given the parameters: temperature, vapor fraction, pressure, composition, and flow rate. So we have been given that in hot side the vapor fraction is 1, the pressure is 5 bar, the flow rate is 100 kg mole per hour, and the composition of water is 1. Water is on hot side, water is on cold side. We need to know the hot outlet temperature. The pressure drop at hot side is 0.1 bar. The flow rate, again, there is no change, and so does in the composition. In the cold inlet, 25 degrees centigrade, 5 bar, 200 kg mole per hour. Obviously, there is water, so mole fraction is 1. And the outlet temperature is 35 degrees centigrade, 4.8 bar, means a pressure drop of 0.2 bar. So let's quickly go to the Aspen Plus and first simulate this process. Obviously, it will not take more than 1 to 2 minutes. So we will do it quickly. We will first add the water as the component, going to all and selecting steam and BS, and then clicking on run. And we will do it very quickly because we have already done this heat exchanger simulation in our previous videos as well. But obviously we have to do it again for the system representation. And I will do the labeling and the connections quickly. So as you can see, the connections have been made: hot inlet, hot outlet, cold inlet, and cold outlet. So we will first specify the hot inlet, and we have been given that the pressure is 5 bar, vapor fraction is 1, flow rate is 100 kg mole per hour, and the mole fraction for water is 1. And now for the cold inlet, we have been given that 25 degree centigrade, 5 bar, 200 kg mole per hour. Mole fraction for water is here is 1. So we have been given water for both hot and cold sides. Now we will specify the heat exchanger specification, and we have been given cold water outlet temperature of 35 degree centigrade. So we will specify cold stream outlet temperature, that is 35 degree centigrade. Minimum approach temperature is 10, and we have been given the pressure drop of 0.1 bar. So we will specify it as minus 0.1 at the hot side and minus 0.2 bar at the cold side. So we will run it, and once after running, we will be getting the results. So once you click on stream results, you get all the results available here as well. But now obviously we have first simulated the process. That was the main requirement before going to the Exergy analysis. So once you have started the Exergy analysis, what you need to do, you need to go to the setup calculation options in Aspen Plus, and you need to specify Exergy reference environment temperature and pressure. So specify it as 25 degrees centigrade and obviously 180 M in the SI units obviously. Then you need to go back to the stream results, but again you need to reset it and run it so that you get all the conditions available at the reference conditions as well. Now you can see there is no Exergy coming over here. So what you need to do, go to this add properties, click on Exergy, and obviously you need Exergy flow rate, because if you select either these, it will give an answer in some other unit, but obviously you want answer in kilowatt. Click OK. OK, it is kilowatt. However, this exergy calculated is physical exergy. It has nothing to do with the chemical part. So obviously we need to calculate the chemical part by using Excel and taking physical exergy from here. So as you can see, the cold inlet, cold outlet and hot outlet, and all the values of physical exergy are pasted over here. Now, if we go back to the formula, the chemical exergy is calculated as summation of Xi, which is the mole fraction, multiplied by standard chemical exergy. So first we will calculate this factor and then we will move to the second factor. So the standard chemical exergy value for water, because we are considering only water in the case, is 9.49 kilojoule per mole. Obviously, once we have more than one components, then we have to also consider the standard chemical exergy value of all components. Now we need to know the mole fraction of all of these and the molar flow rates as well. I will let you know the reason why we are considering the molar flow rate as well. Now as you can see, the mole flow is 200 kg mole per hour for both cold streams and 100 kg mole per hour for both hot streams, and the mole fraction is obviously 1. So first term, that is Xi, which is the mole fraction multiplied by the standard chemical exergy, but if you can see, its unit is kilojoule per mole, and obviously we want the answer in kilowatt. So what we need to do, we need to multiply by its mole flow. So now what it becomes, the mole will cancel out with mole. Let me show it to you, kilojoule per mole, and it will be multiplied by k mole per hour. So once we get now, that is mole cancel out with moles, kilo multiplied by kilojoule per hour. So what we need to do, we need to multiply this kilo with the factor, like we need to multiply it with 1000 as well. So once we multiply it with 1000, it will become kilojoule per hour. But obviously for kilowatt, it should be in kilojoule per second. So what we need to do, we need to divide this factor by 3600. And that's how we calculate this first term in kilowatt. If we do not multiply it with 1000 and divide it by 3600, we will not get our answer in kilowatt. So that's a unit conversion which have been made in the system. Let me repeat it, that first we have multiplied the mole fraction with standard chemical exergy. It has given us answer in kilojoule per mole. It's not k mole, it's single mole. We have multiplied it with kilomole per hour to get answer in kilo multiplied by kilojoule per hour. So that kilo is multiplied with the factor as 1000, so that remains with kilojoule per hour, and then divided by 3600 to get answer in kilojoule per second, and that kilojoule per second is equal to kilowatt. What we need to do, we need to drag it, but obviously before doing that, let's fix this standard chemical exergy value, and we can now simply drag it over here as well. Now we need to calculate the second term of chemical exergy, and that is RT naught. R represents the ideal gas constant 8.314 joule per mole per Kelvin. T naught, the reference temperature 298.15, and Xi, natural log of Xi. So again, R, which is 8.314 298.15 multiplied by Xi multiplied by the flow rate multiplied by natural log of Xi. So we know the natural log of 1 is 0, but obviously we need to understand it for the other systems as well. Now the unit of R is joule per mole Kelvin multiplied by Kelvin and then multiplied by the flow rate, so it will be kilomole per hour. So how it left, kilojoule per hour. So as you can see that mole is cancelled with mole, Kelvin is cancelled with Kelvin, and we are left with kilojoule per hour. So obviously we need to divide that factor once after multiplying by 3600 as well to remain it in kilowatt. Obviously right now its answer is 0. It won't make any effect, but once you are calculating the right terms, or you are calculating the factors where it is not 0, and if you have not divided by 3600, that will cause some problems. So unit should be consistent while you are doing it, yeah, like R T not. So it has given, if you look at these two factors, it has given us joule per mole. So once we have multiplied it with the kilomole per hour, it has left with kilojoule per hour, and then we have to divide it by 3600. So what we need to do, we need to again simply drag it, and we will now sum these two terms to get the answer of chemical exergy in kilowatt. And how we can get that answer? We can get that answer by adding these two terms. And now total exergy is calculated, and obviously for the successful value or for a right value, both the units should be in same. So that is calculated as chemical exergy plus the physical exergy. So that is how the total exergy of a single stream calculated in the system. Now once after doing it, we have to obviously calculate the percentage exergy efficiency for heat exchanger and exergy destruction loss. So once we have to do it, first we'll check what is the total exergy in and what is the total exergy out of the system. Total exergy in is associated with definitely the cold in and hot in, and total exergy out is associated with cold out and hot out. So that is calculated as total exergy of cold in plus total exergy of hot in. Similarly, for outlet, total exergy of cold out and total exergy of hot out. So this is how total exergy in and total exergy out is calculated. Now the formula is very simple, that total exergy out divided by total exergy in multiplied by 100 will give exergy efficiency, and exergy destruction is total exergy in minus total exergy out. So now the formula is very simple, that is equal to total exergy out divided by total exergy in multiplied by 100. So that will give answer of 98.86%. And if we take it to number, 98.86% exergy efficiency of heat exchanger in the current state while it is operating, and the exergy destruction is total exergy in minus total exergy out. So there is a work loss or the exergy destruction of 13.1 kilowatt while operating this heat exchanger. And obviously this is how the exergy efficiencies and exergy destructions are calculated in the system. And obviously, once we have calculated these, we can do the further optimization to increase this exergy efficiency and to reduce this exergy destruction. There is one thing to be noted. This value cannot be greater than 100%, and this value cannot be negative, because the exergy destruction is negative. It means that total exergy in is low and out is high. How this can be possible? So obviously the exergy destruction will always be positive, and the percentage exergy efficiency will always be lower than 100%. So that's how exergy of an equipment is calculated using Aspen Plus, and we are now using Aspen HYSYS for this. So we have been given a compressor data. Stream data is temperature 25 degrees centigrade, pressure 1 atm, flow rate 100 kg mole per hour, and the composition is 79 mole percent nitrogen and 21 mole percent oxygen. And we have to compress it to a pressure of 5 bar. And if we talk about the specific formula for this, the percentage exergy efficiency will be calculated as output stream exergy divided by inlet stream exergy plus energy. This is one of the way to do it. Obviously other formulas are available in literature, but obviously we will get almost the same answer from that. And exergy destruction in kilowatt is calculated as inlet minus outlet. Obviously inlet is feed plus energy and outlet is product. So we will do the calculations, and before doing that we will first calculate physical exergy from Aspen HYSYS. So let's quickly move to Aspen HYSYS and solve the process. So quickly we will add two components, which are nitrogen and oxygen, and then we will add the fluid package, which is Peng Robinson, which is applicable for this system. Going to simulation environment and selecting the compressor and doing the required connections, first changing its name to compressor, and feed air, outlet is compressed air, power produced, and as a result the bar turns yellow. Now we have to specify the properties: 25 degrees centigrade, 1 atm, 100 kg mole per hour, and if you double click it, 0.79 for nitrogen and 0.21 for oxygen, and specifying outlet pressure as 5 bar. And this is how the compressor is solved. This is a very simple procedure to solve the compressor, but the real thing is that how we can specify the reference conditions. And obviously for reference conditions the procedure was very simple in Aspen Plus, and also it is simple in Aspen HYSYS as well. So clicking here, and opening the show correlation manager. This one is clipboard, this one is unit, this one is simulation. So in simulation, clicking on this correlation manager and going to the standard, and in standard scrolling down until you get mass exergy over here, and the reference temperature is 25 degrees centigrade while reference pressure is 101.3 kilopascal. So obviously it is not equivalent to 1 atm, because for 1 atm it should be 101.325 kilopascal. So we will change it as 101.325 kilopascal. So it will be 25 degrees centigrade and 1 atm. So now we will come back here and we will double click on this compressor. We will open worksheet and going to the properties. And if you see in the properties that mass exergy is given in kilojoule per kg. If you remember in Aspen Plus, this exergy was in kilowatt, but here it is in kilojoule per kg. But obviously we can convert it to kilowatt by multiplying by mass flow rate and then converting from kilojoule per hour to kilojoule per second. So we have to copy paste these two exergies. These are the physical exergies. Again, these are not chemical exergies. We have to calculate chemical exergy from Excel sheet. So we will copy. Now what to copy? Obviously the mass exergy, which is in kilojoule per kg. Going to the conditions, the mass flow rate, which will be required for conversion to the kilowatt of physical exergy, and we need mole flow rates and molar composition, which will be required for the chemical exergy. So we have copy pasted all the data here in Excel sheet, and if you see exergy kilojoule per kg, flow rate kg per hour, and now we have to convert it to physical exergy of kilowatt. And how we can do it? We have to multiply exergy with flow rate, and it is currently in kilojoule per hour, divided by 3600 to convert it to kilojoule per second. And again, even copy pasting, and it is 157.23. So kilojoule per second gives us the answer of kilowatt. So this is how physical exergy is calculated. Now we have to calculate the chemical exergy part, and as we have seen before, there are two terms which are associated with it, and one of the term includes the standard chemical exergy. So we have to calculate the standard chemical exergy, or we have to take from literature these two values. So as you can see, the standard chemical exergy of nitrogen is 0.72 kilojoule per mole, while that of oxygen is 3.97 kilojoule per mole. So we have to now calculate the chemical exergy. And so for chemical exergy calculation, we will be first needing the mole flows and molar composition. That the flow rate is 100 kg mole per hour for both air streams. Mole fraction for nitrogen and oxygen remains the same in the process because it's simple compression, there is no separation. So 0.79 and 0.21 for both. Now we have to calculate the first term, the chemical exergy term number one. We have to calculate it. How we can calculate it? That we have to multiply this flow rate with the mole fraction and with this kilojoule per mole. So for a single component, this was our procedure. And if you see, this is 56.88, but that is in currently kilo multiplied by kilojoule per hour. Obviously, we have to multiply it with 1000 and divide by 3600 if you remember the previous lecture as well. However, this was for a single component, and for two components, what we need to do, there are different aspects as well. You can apply some product formula as well. But again, I'm keeping it simplified. So flow rate multiplied by the composition and multiply its relevant chemical exergy. So again, calculating it, and now you can multiply it with 1000 and divide by 3600. So converting it to number and making sure that once you drag it, the terms do not change. So applying or fixing this G cell as well. And now you can simply drag it, and obviously the chemical exergy for these two will remain the same, the term number one, because of the fact that there is no separation. These terms might change, or obviously definitely change, when there is a change in composition because Xi factor is involved in the system. Now we will calculate the chemical exergy term number two, and how it is calculated as, if we see again, RT naught summation Xi natural log of Xi. So 8.314 multiplied by 298.15 multiplied by flow rate, if we take it like that, flow rate multiplied by the composition multiplied by natural log of composition. This closes the first term, then plus molar flow rate multiplied by the composition multiplied by the natural log of composition. So closing it down, and it has given answer in this. Obviously we have to divide that answer by 3600 to get answer in kilowatt, because all the units should be consistent in the system as well. And again, dragging it, and the same answer for that term as well. So now we have to calculate the chemical exergy in kilowatt, and if you can see chemical exergy in kilowatt, that is adding these two terms in the system. So that's how the chemical exergy is calculated for compression system or for a stream of a compressor system as well. Now we have calculated physical exergy, we have calculated chemical exergy. We have to simply add these two exergies to get our required exergy value, which is total exergy in kilowatt. But again, make sure all these exergies are in same unit, because if these are not in the same unit, these will lead to incorrect answers. And obviously, the energy value is also important in the system. So if we take it like this and just dragging it like that, for feed air, the total exergy is 3.57 kilowatt. For compressed air, which is at the outlet of compressor, is 160.8 kilowatt, and energy required is 185.19 kilowatt. It's already in kilowatts, so there is no need to change it. Now we have to apply the formula, and the formula, I have told you that there are different formulas available in the literature. That percentage exergy efficiency is outlet air exergy minus inlet air exergy divided by the energy and multiplying by 100. So it gives answer in 84.9 as exergy efficiency. And exergy destruction, if we can calculate it, how it is calculated, like it is in percentage, and we have to calculate kilowatt, that is inlet. So what is in inlet? Feed air plus the energy minus compressed air. So 27.96 kilowatt of exergy is destructed in the process, while the exergy efficiency of the process is 84.9%. And then there is another formula to calculate the exergy efficiency, which I have shown in the slides, that compressed air, which is outlet, divided by inlet. So that is another way of calculating the exergy efficiency. But you can see the exergy efficiency is slightly high for the second formula. Obviously, you cannot use the same nomenclature across each combination. So for compressor, the most widely used formula is that outlet air exergy minus inlet air exergy divided by the total work required multiplied by 100. However, the exergy destruction for both cases will remain the same because it is simply inlet minus outlet. So that's how exergy efficiency is calculated using Aspen HYSYS, that we have taken physical exergy, but again in a different fashion. Like in Aspen Plus, we got exergy directly in kilowatt. Here we have to convert it to kilowatt. Then we have taken two components, and again we have seen the overall procedure for both components as well. And then we have checked how exergy efficiency is calculated for a compression system. This was a slight complex example as compared to the heat exchanger because we have included two components. But again, separation system is not involved, because once separation system is involved, the exergy values changes. As you can see, the term number 1 is same for both streams, 2 is same for both streams, and even chemical exergy is same for both streams. But when separation system is included, this does not happen. So in the next video or in the upcoming videos, we will be discussing the separation system exergy efficiencies as well. So that's it from this lecture. Thank you so much. Please do watch, like, share the video, and subscribe to the channel Aspen Tech. Till then, it's goodbye. Stay tuned.